Hello everyone. Today we will be presenting quantum 3D infrared imaging without infrared camera. Quantum optics has allowed us to surpass the classical limits in many different ways. One intriguing approach is quantum imaging with undetected photons. So it's based on a phenomenon known as induced coherence, where two pairs of entangled photons are generated at nonlinear crystal number 1 and number 2. If we align the two either modes such that they are completely indistinguishable and then detect the signal photons, an interference pattern occurs at the detector because the source of the signal photons are completely indistinguishable. However, if the first either is blocked and we perform coincidence measurement, we can now distinguish the source information and the interference pattern disappears. We now extend this phenomenon to 2D and fold the two crystal setup into one. Our laser illuminates our nonlinear crystal and produces a pair of entangled photons. The idler mid-infrared photon traverses the bottom path and probes the sample, whereas the signal visible photon does not. They are both reflected back to the crystal, producing the second pair of entangled photons. However, we detect only the signal photons on our detector, achieving mid-infrared imaging using standard silicon-based detectors. This is very important for biological samples because visible light perturbs its natural processes. To take this a step further, we extend this to holography to achieve 3D imaging where phase and transmission are simultaneously measured. However, the biggest issue in holography is phase wrapping. For example, this sample has a longitudinal thickness that corresponds to 3.5 wavelengths, but the phase measurement will only give half a wavelength. We can never know the true thickness of a sample from this measurement. This is very crucial for biological samples such as red blood cells that have a thickness of much greater than one typical Idler wavelength. Therefore, we propose multi-wavelength quantum holography in which we spectrally filter and select two or more wavelengths before the detector and use the effective wavelength to create non-phase wrapped 3D images of our object.
Now we experimentally demonstrate the imaging capability of the system. We image an etched photoresist sample with 7.7 micron and optical path difference, and it's definitely not measurable by any single wavelengths. A sample image is shown on the top right. On the left-hand side, we have the 710 nanometer interference pattern. On the right-hand side, we have the 720 nanometer interference. And shifting the mirror in one arm, like doing so, actually changes the interference condition. And we analyzed, for example, an intensity at one specific location. We see that on the x-axis is the mirror shift. We see the intensity changes as a sinusoid with the mirror shift. And for interference pattern like this, we're able to use phase shifting holography to retrieve the phase and intensity profile simultaneously. And these are the four images used for retrieving the phase and intensity profile. They correspond to four phase conditions as shown on the top right. And the phase profile and intensity profile are shown here. And if we analyze the two phase profile measured by two wavelengths, by using their difference or this equation, we're able to compute the true optical displacement induced by the sample, and that is measured to be 6.8 micron, and which correspond a real dimension of 2.1 micron, and that's within and the 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 true value or the ground truth measured by a profilometer is within the uncertainty bound. Also, the transmission is also obtained. For example, if we look at the 720 picture, we measure the photoresist transmission to be 0.96 plus or minus 0.06. And the ground truth is actually 0.918, and that's also within the uncertainty bound. So in this study, we achieved quantum imaging with non-interacting photons. We're able to probe the infrared response of samples, which is very important for biological applications, by using a room temperature standard CMOS camera. And we're able to retrieve the phase and the transmission profile simultaneously. Most importantly, we extended the maximum measurable distance or thickness by 25 times to 50 micron instead of 2 micron, and that can accommodate more biological samples. And we also achieved dual wavelengths or dual spectral imaging. And this study can be easily extended to more than two wavelengths. And thank you very much for your attention.